September 1977. High atop the most powerful unmanned rocket in America's arsenal sits not a weapon of massive destruction, but a once-in-a-lifetime chance for massive discovery. For the past 15 years, unmanned spacecraft have been paving the way for manned expeditions, and although the Apollo program is long over, unmanned missions continue to reach higher and farther than ever before. Voyager 1 and her sister ship, Voyager 2. Identical twins to be launched on identical rockets only 16 days apart. They will fly together to the outer solar system, passing Mars and the asteroid belt to visit the king of planets, Jupiter, and use its gravity to visit the crown jewel of the solar system, Saturn. This complicated maneuver has only been done once before, and it's known as a gravity assist. Mariner 10, 3 years earlier, used Venus's gravity to alter its direction of travel, aiming it at the planet Mercury. But the Voyager mission doesn't simply plan to use one gravity assist, it plans to use 3. 13 years earlier, physicist Gary Flandro, working at the NASA Jet Propulsion Laboratory, noted in his computer calculations of planetary positions in the near future that a rare window would open in 1977. A quintuple planetary alignment will occur between Earth, Jupiter, Saturn, Uranus, and Neptune. A solar system event that only happens every 175 years. The last occurrence being in 1802, as Napoleon Bonaparte swept his armies across the plains of continental Europe. That year, the existence of Neptune hadn't even been discovered yet. Now, in 1977, as humanity is just beginning to enter the age of interplanetary spaceflight, this quintuple transfer window provides NASA with a goldmine opportunity. The opportunity to visit 4 separate planets with a single rocket launch. NASA and the scientific community are so roused by this idea that they decide to launch not one mission, but 2, simultaneously, to take advantage of this circumstance. 2 missions, however, is actually a downgrade from the original concept outlined in 1964, which called for 4 simultaneous missions. The 2 Voyager probes have a relatively simple and highly ambitious goal: to survey and explore where no mission had dared to go before. It is a well-known fact before the launch of the 2 Voyagers that negotiating the space environment around Jupiter and Saturn will bring challenges yet to be faced by humanity, including passing through both planets' incredibly powerful magnetic fields, as well as traversing and exploring their ring systems. So, 2 smaller probes, with incredibly simplistic and rudimentary science capability, are sent to Jupiter and Saturn 5 years before the launch of the Voyager probes, to ensure that nothing unseen could potentially damage the incredibly sophisticated and sensitive instruments aboard Voyager. These 2 probes are respectively called Pioneer 10 and Pioneer 11. They both fly by Jupiter in 1972 and 1974. Pioneer 11 will go on to fly by Saturn in 1979, 2 years after the launch of Voyager. These 2 small probes will not go on to visit Uranus or Neptune, but they blaze the trail for the ultimate adventure that is about to begin. The construction of the Voyager probes is a slow and thoughtful process, as the importance and symbolism of this mission does not go unnoticed. Voyager 1 and Voyager 2 are 2 separate vehicles, but they house incredibly similar scientific instruments, each probe acting as a check on the other to validate its data, and also serving as an in-flight backup if any one of the 2 probes fails during the course of the 1.5-decade-long foray into deep space. Each Voyager probe consists of a decahedral central body, 47 centimeters high and 6 feet across. A 12-foot wide parabolic antenna will be mounted on top of this central body, known as the bus. The major portions of scientific instruments will be mounted on 2 spring-loaded booms, or extendable arms, that will be deployed once the probe is already in space. These first and second booms are some 8 feet long. The third boom, however, is some 42.5 feet long, and contains on the very end Voyager's power supply. 3 radioisotope thermoelectric nuclear generators, with a 66-pound piece of plutonium-238 inside each one. These 3 rocks of plutonium will undergo radioactive decay during the flight, and as they do, they will radiate heat. This heat will be absorbed by a bimetallic thermal conductor that will convert it into electrical power for the onboard systems of the spacecraft. Nuclear power is preferable over solar power when traveling so far from the sun. The 3 radioisotope nuclear generators, known as RIT-Gs, are located very far away from the spacecraft on the end of a 42-foot-long boom so that they do not interfere with any of Voyager's onboard science instruments. As the radioactivity of the fuel decreases over time, so will the amount of heat given off. Over the course of its lifetime, the electrical supply of both Voyager spacecraft will slowly dwindle to nothing, over 51 years, provided nothing else goes wrong. The electrical output at launch is approximately 470 watts of 30-volt DC power. Data can be stored on board the Voyager probes with the help of a small digital tape recorder, but only temporarily. Any and all data taken by the Voyager probes will be quickly, if not immediately, transmitted back to large radio telescopes located on Earth. The download speed from Voyager is 7.2 kilobytes per second. Voyager, because of its planned distance from Earth and the resulting delay in communication, is designed with 1970s technology to operate in a highly autonomous manner. To do this, 3 interconnected onboard computers are utilized. The first computer, known as the Computer Command System, is responsible for storing commands for the other 2 computers and issuing those commands at set times in the mission. These commands are programmed years, even decades in advance. Each Voyager probe has the same 4 scientific objectives. 1. To investigate the circulation, dynamics, structure, and composition of a gas giant's atmosphere. 2. To characterize the morphology, geology, and physical state of as many moons of said gas giant as possible. 3. To provide improved values for the mass, size, and shape of each gas giant, its rings, and any moons. And 4. To determine the magnetic field structure and characterize the composition and distribution of trapped particles and plasma therein. The majority of instruments aboard Voyager 1 and 2 primarily deal with magnetic field research and cosmic rays. Instruments on board include several visual light spectrum cameras, infrared spectrometers which will determine atmospheric composition and thermal properties of the planets. Ultraviolet spectrometers will measure radiation properties of the planets. Triaxial magnetometers will investigate the solar wind interaction and accurately map out the magnetic field of the gas giants. Plasma spectrometers will detect the density of charged particles colliding into Voyager during its flight. A major goal of the Saturn flyby is to closely study the moon known as Titan, which is the only moon in our solar system with its own atmosphere. To this end, whichever probe reaches Saturn first will fly very close to Titan, negating an opportunity to visit Uranus or Neptune and sending it into a high latitude inclination of the solar system with escape velocity. If this is successful, the second probe to visit Saturn will instead ignore Titan and use Saturn's gravity to set it on a course to Uranus. Some engineers even begin to float the idea of ignoring Titan overall for a chance to visit one of the probes to Pluto, but Titan is considered a more interesting and promising scientific target. Because of a minor glitch in Voyager 1's computers, Voyager 2 launches first. Voyager 1 follows only 16 days later. The Titan IIIe launch vehicles that will propel the Voyagers into their initial journey towards Jupiter are among the most powerful unmanned rockets the U.S. has to offer in the year 1977. Like the upcoming space shuttle, their first stage of flight is predominantly powered by solid rocket boosters, which cannot be shut down or throttled. At the moment of ignition, on September 5th, 1977, the fate of Voyager is forever sealed as mankind's ultimate ambassadors to the universe begin their long journey forward into the unknown.
The Titan core vehicle consists of a liquid-propellant two-stage rocket and utilizes an unsymmetrical dimethylhydrazine for fuel with nitrogen tetroxide as the oxidizer.
As the Titan III's upper stage shuts down for the final time, Voyager 1 separates and uses its onboard reaction control system thrusters to perform an about-face. The onboard science instruments are calibrated using the Earth, and as Voyager 1 gazes longingly back at the home planet of her creators, she's already departing the Earth-Moon system for the final time, never to return again. Voyager 1 is traveling slightly faster than Voyager 2 and passes the Moon only 15 hours into the flight. Despite being launched more than 2 weeks later, it overtakes it on the 15th of December, 1977. The two Voyager probes remain silent and steadfast on their journey outward, and for a year and a half, humanity waits. On February 10th, the science instruments aboard Voyager 1 are powered up for a second time after nearly a year in hibernation. Its eyes are open and ready to be greeted by the king of the planets, Jupiter. Before anything is seen, however, much is heard. While Jupiter is still but a tiny speck the size of a thumbnail in Voyager 1's sky, she passes the bow shock of the magnetic field, and the magnetometers detect this rapid and wild change immediately. Jupiter's magnetic field is 20 times stronger than that of Earth's, and is some 3.6 million miles wide. As Voyager 1 approaches Jupiter, it takes one photograph every 9 hours and 57 minutes, the length of a Jovian day. It makes its closest pass to Jupiter on March 5th, 1979. As Pioneer 10 and 11 did, Voyager 1 observed several counter-rotating cloud bands distributed among Jupiter's latitudes, indicating that Jupiter's weather system is an incredibly active one. Jupiter is spinning at an alarming rate. The entire planet spins once every 9 hours and 59 minutes, and wind speeds within its cloud bands can reach 400 miles per hour. These cloud bands are colored thanks to the elements which comprise them. Reddish clouds of ammonia intermix with the yellowish hydrogen that predominates the planet's complexion, forming incredible hurricanes, the most famous of which is the Great Red Spot. This single hurricane was observed more than 300 years ago in the time of Galileo, and is still raging today, some 1.3 times wider than the Earth itself. Jupiter is the king of all the planets. As Voyager 1 passes by, it's traveling faster than ever before, nearly 38,100 miles per hour, nearly 10 miles every second. This incredible speed is due to Jupiter's overwhelming gravity, which is directly correlated to its humongous mass. Jupiter's mass is 2.5 times that of every other planet in the solar system combined. and its gravitational pull is so strong that the center of gravity between Jupiter and our Sun lies outside of the Sun. That is to say, the Jupiter doesn't orbit the Sun. The Sun and Jupiter orbit each other. While incredibly massive, Jupiter is mostly volume, not density. It is 1,300 times the size of the Earth, but only 310 times more massive. This is because Jupiter is comprised mostly of hydrogen gas, the lightest element on the periodic table. Jupiter is so massive that any more significant matter added may cause the temperatures and pressures deep inside the core of this gurgling gas giant to rise to a point high enough to facilitate nuclear fusion, allowing Jupiter to become a second star. Current theories hold that Jupiter and our Sun are the oldest two celestial bodies in the solar system. They were both competing for dominance, gobbling up all the matter they could in the protostellar period of time that precluded our own star's birth. The celestial body that would go on to become the Sun won out in the end, and Jupiter's inability to gain more mass or size prevented our solar system from becoming a binary star system, like a very large percentage of all the stars in the Milky Way. Jupiter's importance did not end there, however, as it ended up playing an incredible role in shaping the solar system we know today. As Jupiter grew larger, so too did its collection of small satellites and moons. As of 2017, Jupiter has a confirmed 70 moons, and it's gaining new ones all the time. Most of these are simply small asteroids, but 4 of them are much larger than even our own moon. These 4 moons, visible to telescopes on Earth, were discovered in 1610 by Galileo Galilei, and are rightfully called the Galilean moons. As Voyager 1 shoots through the Jovian system, it uses its telescopic cameras to photograph all 4 of these unique, dynamic celestial bodies. First, there is Io, the innermost of the 4 Galilean moons. It has the highest density and the least amount of water of any known astronomical object in the solar system, frozen or otherwise. Io is a world of geologic wonders, but it has no atmosphere. Over 400 active volcanoes dot its surface and are constantly spewing out matter from Io's insides, 24 hours a day, 7 days a week. Io's volcanic plumes and lava flows produce large surface changes and paint the surface in various shades of yellow, red, white, black, and green. This is because Io's surface is comprised primarily of silicate rock and iron, with large amounts of sulfur and sulfur dioxide. Io is a toxic world. It orbits so close to Jupiter that it makes a complete circle around the gigantic planet once every 42 hours. Gravitational tidal forces from Jupiter are so strong on Io that they literally rip it apart from the inside out, generating the energy required to sustain Io's many volcanic eruptions. Io's surface is covered in smooth plains dotted with tall mountains and pits of various shapes and sizes. At least 9 of the 400 active volcanoes on Io are directly observed by Voyager 1. Volcanic eruptions from Io are so violent that some of the matter from inside manages to achieve escape velocity, and Io leaves a trail of frozen lava behind it as it orbits its planet. Some 200,000 miles further out from Jupiter than Io lies the second Galilean moon, a mysterious and frosty ice world known as Europa. Slightly smaller than Earth's moon, Europa is made of silicate rock and has a water-ice crust. It has a minuscule atmosphere that's essentially a vacuum, and a surface that's oddly striated by cracks and streaks, with little to no impact cratering. Europa has the smoothest surface of any known solid object in the solar system. These cracks are indicative of plate tectonics, which can only be powered by one thing: heat from below. Europa is located twice as far from Jupiter as Io is, and calculations done indicate that the tidal forces from Jupiter would not be strong enough to melt rock. So why then, if tidal forces cannot melt rock, Does Europa exhibit signs of moving crust plates? Well, although the tidal forces may not be able to melt solid rock on Europa, they would be strong enough to melt subsurface ice. If a large portion of Europa's lower crust is comprised solely of water ice, it could be melted from the gravitational forces from Jupiter, forming a vast subsurface liquid water ocean that has never seen the light of day. Estimations made place this liquid water ocean some 50 miles under the surface. Portions of the crust of Europa are observed to have undergone a rotation of nearly 80 degrees, which would be unlikely if the icy crust were solidly attached to the mantle. Europa's crust is estimated to be only between 20 and 180 million years old. Radiation from Jupiter's magnetic field on the surface of Europa exceeds 540 rem per day, an amount that would cause severe illness and death in human beings if exposed to for more than 24 hours. But 50 miles of ice is more than enough radiation shielding for any potential ocean below. Brown linea on Europa's surface are produced from tidal flexing from Jupiter, and exhibit properties similar to mid-oceanic ridges found on Earth. Europa's outer crust is comprised of water ice, but this is some 260 degrees below zero, keeping the solid ice as hard as granite. As Voyager 1 passes Europa, it observes water vapor plumes in the space around Europa, which are thought to be caused by erupting geysers on its surface. No geysers are actively observed by Europa by either spacecraft, however. As Voyager 1 climbs away from Jupiter, it passes the third and largest Galilean moon, Ganymede. Located some 665,000 miles away from the Jovian atmosphere, Ganymede is comprised of approximately equal amounts of silicate rock and water ice, and is 8% larger than the planet Mercury. It is also the only moon in the solar system to have an appreciable magnetic field of its own. Ganymede's powerful magnetic field can only mean that its iron-nickel core is partially molten. Like Europa, Ganymede is thought to have a subsurface ocean. In fact, Ganymede's subsurface ocean is much larger than Europa's, and possibly even larger than Earth's oceans. Ganymede's mass and composition, with over half of the planet being comprised of water, places its subsurface ocean anywhere between 300 and 500 miles deep, dwarfing Earth's Mariana Trench, which is only some 7 miles deep. Unlike Europa, Ganymede's subsurface ocean is located under some 80 miles of solid rock, making it much more inaccessible than even Europa's 50 miles of solid ice. Finally, Voyager 1 passes the outermost Galilean moon, Callisto. Slightly larger than our own moon, Callisto is larger than Europa and Io, but not Ganymede. Callisto has 99% the diameter of the planet Mercury, but only a third of its mass. The surface of Callisto is the oldest and most heavily cratered in the entire solar system, completely covered with impacts. It doesn't show any signatures of subsurface processes such as plate tectonics or volcanism, with no signs that geologic activity of any kind has ever occurred, a rarity for a celestial object this size. Because of Callisto's distance from Jupiter and location within Jupiter's magnetic field, radiation levels on the surface are incredibly low. This makes Callisto an ideal target to build a surface base in the future for long-duration habitation. Like Ganymede, Callisto may have subsurface oceans that help power its weak magnetic field, but evidence for this is slim. The two Voyager space probes made a number of important discoveries about Jupiter, its satellites, its radiation belts, and never-before-seen planetary rings. The gravitational assist trajectories at Jupiter were successfully carried out by both Voyagers, and the spacecraft systems are once again powered down, and the probes are put into hibernation. Jupiter may not have become a second star, but it was instrumental in forming our early solar system. One important theory on the formation of how life formed on Earth holds that Jupiter's gravity caused the other gas giants, Saturn, Uranus, and Neptune, to be flung further away from the sun than they had originally existed, causing them to pass through asteroid-dense areas of space, sending asteroids and comets to the inner solar system. This period, which took place some 3.8 billion years ago, is known as the Late Heavy Bombardment, and is recorded as a period of massive inner solar system asteroid impacts on the Moon, Mars, and Venus, possibly transforming their environments into how they are today. It is known that both Venus and Mars once had vast amounts of liquid water on their surface. Did the Late Heavy Bombardment, facilitated by Jupiter, seal their fate? Life on Earth is thought to have evolved thanks to amino acids that we know exist on comets and asteroids in the Kuiper Belt, asteroids that may not have reached Earth if not for the gravitational forces of Jupiter. In November of 1980, the probes are turned on once again after many months of coasting in deep space, and open their eyes to witness the wonder child of the gas giants, Saturn. On November 12, 1980, Voyager 1 passes within 77,000 miles of Saturn's cloud tops. Voyager 1 discovers that 7% of the volume of Saturn's upper atmosphere is helium, while almost all the rest of the planet is hydrogen. Saturn may look peaceful and serene, but don't let its monotonous color fool you. The winds on Saturn are much faster than those on Jupiter, reaching a peak of 1,100 miles per hour near the equator. Most of Saturn's hydrogen is not gaseous, however. Several hundred miles below the top of its atmosphere, the hydrogen is compressed into a superconducting liquid, which facilitates both Saturn and Jupiter's powerful magnetic field. Saturn is some 95 times more massive than Earth, but this is all volume. Being comprised of mostly hydrogen, Saturn is the least dense planet in the solar system. And if the entirety of Saturn could be contained within a glass marble, that marble would float in a tub of liquid water. Saturn, like Jupiter, has many, many satellites. Over 62 moons are confirmed to be orbiting Saturn, but by far the most iconic satellite of Saturn is its ring system. Saturn's rings are most likely the result of a large moon in the distant past that came too close to Saturn, passing what is known as the Roche limit, the point at which tidal forces disintegrate a moon. The matter that comprised this moon then strung out over millions of years, finally forming a uniform series of rings comprised of fine particles of dust, rocks, and ice. These rings are some 150,000 miles across, but are an astonishing 65 feet wide. By celestial terms, this is razor thin. If not for some of the innermost moons acting as gravitational shepherds, these individual rings would continue expanding outward forever. It is at this point that the two space probes, Voyager 1 and Voyager 2, departed on their own unique journeys. Voyager 1's trajectory is altered prior to its Saturn flyby so that it can pass closely by the moon Titan, which, in 1944, was confirmed by astronomers to have its own atmosphere. Images taken by Pioneer 11 in 1979 had indicated that the atmosphere was substantial and complex, further increasing interest. The Titan flyby occurs as Voyager 1 enters the system, and Voyager 1 approaches to within 4,000 miles of Titan. Passing behind Titan as seen from Earth and the Sun, Voyager's measurement of the atmosphere's effect on sunlight determined the atmosphere's composition, density, and pressure. Thick haze over Titan prevents any visual observation of the surface, but the measurement of the atmosphere's composition leads to speculations that lakes of liquid hydrocarbons could exist on the surface, speculations that would later be confirmed in future missions. Titan is the largest moon of Saturn, and its atmosphere is relatively similar to Earth in terms of density. Titan's atmosphere is actually thicker than Earth's, with a surface pressure of 1.45 times that of sea level on Earth, or approximately 21 pounds per square inch. This is by all means survivable for humans without a pressure suit. The atmosphere of Titan, like Earth, is primarily nitrogen. The climate includes wind and rain, though not driven by water. Titan's clouds are comprised of methane and ethane. It has large lakes similar in size to the American Great Lakes, comprised entirely of liquid ethane on its surface. Titan has hundreds of times more natural gas and other hydrocarbons than all the known oil and gas reserves on Earth. But unlike Earth, these hydrocarbons were not formed by biological means. Instead, over millions of years, methane molecules in the upper atmosphere were bombarded by ultraviolet radiation from the sun, turning them into ethane and causing them to rain down on the surface. Titan does, however, contain a huge amount of organic compounds formed from chemical reactions between its methane and nitrogen. Titan is identical to a primordial Earth in all respects except heat. Titan, unlike a primordial Earth, is incredibly cold. Its surface temperature is negative 290 degrees Fahrenheit. Any life that could exist on Titan would need to be both anaerobic and able to sustain temperatures much lower than have ever been found on Earth. The coldest life on Earth are sheets of algae that begin to die at minus 13 degrees. Life on Titan, similar to that on Earth, would have to exist near a volcanic vent, if any exist, for a source of heat. It is possible, however, that life has evolved on Titan beyond our ability to conceptualize it here on Earth. Voyager 1 also photographs the Saturnian moon Enceladus, which is remarkably similar to Europa in its makeup. Although data from Voyager 1 on Enceladus is limited, future missions such as Cassini would go on to discover that Enceladus has over 100 active liquid water geysers, positive proof that a subsurface ocean exists below its icy crust. Voyager takes long-distance photographs of other small moons, such as Tethys, Dione, and Mimas, which wows Earthlings with its Death Star-like appearance. Voyager 1 ceases observation of Saturn on December 14, 1980. With its flyby of Titan complete, it has been shot into a northern inclination, well above the plane of the ecliptic, and making it unable to accompany its sister probe, Voyager 2, onto Uranus and Neptune. Voyager 1's interplanetary journey ends here, but its interstellar mission has only just begun. The Voyager 1 interstellar mission was declared on January 1st, 1981, and since that time, it has continued to look back on our solar system and make observations from incredibly afar. 9 years after leaving Saturn, on February 14th, 1990, Voyager took a snapshot of the light being reflected off of Earth, making the famous image now known as the pale blue dot. The Earth as it truly is. 8 years after that, almost to the day, on February 17th, 1998, Voyager 1 overtakes Pioneer 10 as the most distant artificial object from Earth. Voyager, save for the invention of faster-than-light travel, will always hold that record, now and forever. In 2003, still communicating with Earth, Voyager had passed the outer edges of the Kuiper Belt and was entering the termination shock. This is the point in the sun's magnetic field where the charged particles emanating from our star slow down past the speed of sound. 3 years later, in 2006, Voyager noticed that the ionized particles traveling alongside it began to move perpendicular to Voyager's own movement, and it was at this point that it had entered the heliosheath, the point at which charged particles from the sun are blunted by the interstellar wind generated by all the other stars in our galaxy, and are pushed aside like a magnetic windscreen. Finally, in late 2012, the ionized particles around Voyager seem to have settled into a steady and constant stream, indicating that there is no longer any interaction between the particles around Voyager and our Sun. The ramifications of this simple fact are incredibly far-reaching. Voyager 1 has traveled such a long distance from our sun that it could no longer detect its magnetic field. Voyager has officially entered interstellar space, the space between stars. Voyager 1 is currently traveling faster than Pioneer 10, 11, and Voyager 2. It is many times as far from the Sun as Pluto, and is currently 10,900,000,000 miles from Earth, or about 16.5 light hours, and is gaining distance. Amazingly, we can still talk to Voyager 1, and as recently as last year we powered up its RCS thrusters to realign its transmitter to Earth. Provided it doesn't smash into any interstellar celestial objects, Voyager 1 is forever destined to wander the Milky Way, and will pass as close as 1.3 light-years to a nearby star, Gliese 445, in 40,000 years. Each Voyager probe has, mounted to one of the sides of the bus, a 12-inch gold-plated copper record. This record has recorded on it sounds and images of the Earth, designed to portray the diversity of life and culture on our planet. Each disc is encased in a protective aluminum jacket which itself has illustrations relevant to humanity and our solar system at large. Each record comes with a cartridge and a needle. Famous music from human history, such as Bach and Mozart, is located on this record, as well as greetings in over 55 languages, 35 common sounds of life, both natural and man-made, and scientific diagrams detailing the solar system, the development of human embryos, our knowledge of chemistry, mathematics, and DNA, the building block of life, as well as Earth's location within the solar system, and our Sun's location in relation to the 12 stars nearest to us. Any and all indications to demonstrate to any potential discoverers of the Voyager probes, millions of years from now, perhaps billions of years, that we are here, we are alive, and we are intelligent. Most importantly, a small piece of uranium-238, with a radioactive half-life of some 4.5 billion years, as old as the solar system itself, is electroplated on the aluminum case of each record. Any alien civilization with a fundamental knowledge of chemistry will be able to determine the precise time at which Voyager was launched based on the progression of this uranium's decay. The records were designed for playback at 1,000 RPM. The Voyager space probes are, beyond anything we've ever done as a species, humanity's permanent imprint on the universe. They will last longer than Homo sapiens, than the Earth itself, than even the solar system. For billions and billions of years, these two husks of circuitry and metal, nicknamed Voyager, will continue to do just that. Voyage out on an incredible journey across the stars, forever moving forward in the spirit of unbridled curiosity that has cultivated the essence of human exploration since time immemorial. These have been the Voyagers.